Hello everyone, in this video we are going to start the problems related to the bending. So this is the first problem from the chapter of bending, which is 6th chapter in the book of Mechanics of Materials by R.C. Hibbeler. So in this problem we are being asked to draw the shear and moment diagrams for the shaft given. So as you can see that there is a shaft, and that shaft is supported on the two bearings at point A and point B, and it is being told to us that these bearings exert only vertical reaction to the shaft, and there is a third force which is acting due to the belt, which you can see is acting downward, has a magnitude of 24 kilonewton. So let's start solving this problem. So in order to draw the shear and moment diagrams, we should know all the forces acting on the shaft. The one force is given, which is 24 kilonewton. The other forces are in terms of the reactions at point A and point B. So therefore we have to first calculate the reactions, the vertical reactions actually at point A and point B. So let's consider the shaft. So there are two reactions are there at point A and point B, and let's represent them with RA and RB. Let's shift to the shaft. The third one is 24 kilonewton acting at the left end, and these are the dimensions. Let's name the left end as C, the other are point A and point B. So now we have the free body diagram of the shaft. Now let's move on for the calculation of RA and RB. Now for determination of RA and RB, we need to apply the conditions of equilibrium. Let's first apply the second condition of equilibrium, that's summation of all forces acting vertically are in y direction equal to 0, taking the upward forces as positive. So we have one force acting downward, which is in a magnitude of 24 kilonewton, so that will be negative. The other two are RA and RB, both are acting upward, so positive RA, positive RB equal to 0. So in this equation we can see that there are two variables are there, and we cannot calculate any of the variable. Therefore we now need to apply the third condition of equilibrium, that is summation of all moments acting at any point equal to 0. Let's consider the point as B. We can also consider point A. Both will result into one of the reaction force. I'm taking point B, and I'm taking all clockwise moments as positive. You can also take the anti-clockwise moments as positive, which is usually the case in most of the books, but it's again up to you. So this 24 kilonewton force will cause the anti-clockwise moment, so negative. As you know that moment is actually the force multiplied by the moment arm. So force is 24 kilonewton. How about moment arm? The moment arm will be the distance between the line of action of force and the point about which you are calculating. So that perpendicular distance is actually 800 plus 250 millimeter. It's better to convert into meters. This is 0.8 meter. As we know that in 1 meter we have 1000 millimeters, and this 250 millimeter would be 0.25 meter. So then we will have the momentum as 1.05. Now RA will be causing the clockwise moment about point B. You can see like the moment will be like this, so clockwise, and it's positive. RA multiplied by the momentum, which is 0.8 meter, is equal to 0. So this negative value shifting on the other side will become positive, and this 0.8 is multiplied with RA, and if we shift on the other side, that will be in the division. So as a result of the calculations, you're going to get the value of RA as 31.5 kilonewton. So this RA is actually 31.5 kilonewton. Now if we just put RA value into this equation, so this equation then yields. So as a result of this simplification from this equation, we will have value of RB as minus 7.5 kilonewton. Now what that minus implicates, the assumed direction of RB, which was upward. Now the value that came out to be negative 7.5, that means the direction will be opposite to the assumed. So we have assumed upward forces, it's actually a downward force. So you can write RB as minus 7.5 kilonewton if you are showing the direction upward. Obviously we have done the calculations and we come up with the value of RB as negative, which shows that the direction of RB should be downward. So instead of upward, it's actually downward. Now you can change the sign. Now we know the magnitude of all the forces acting on this shaft.